Okay, so another example for gas mixture. What we have here, we have two separate tanks which are connected with a pipe. At the beginning, the valve on the pipe is closed, so we have two completely separate tanks. And the pressure as well as the temperature of each gas is given. On the left hand side, we have nitrogen. On the right hand side, we have CO2, carbon dioxide, and the pressure is given, the temperature is given, and also for each gas, the mass of the gas is given. All right. So the problem statement pretty much explains the same thing. Here it says the valve on the pipe is opened, like this thing is opened, and the two gases mix with each other. So the final temperature is given at 23 degrees C. The question is asking for the volume of the each rigid tank as well as the final pressure. You know what? This problem is exactly similar to a previous problem that we did. We had two compartments in a tank, in a rigid tank, which were separated by a membrane. So the concept behind them are exactly the same. What we have here, we have two completely isolated tanks in state 1, and in state 2 the valve is open, so we have one big tank, one dumbbell shaped tank, which has a mixture of nitrogen and CO2. So for part A, we need to find the volume of each tank, and quite frankly that is pretty simple. We can just utilize the ideal gas law. So the ideal gas law says PV equal to RT. Okay, I'm applying that for the left tank. So pressure is given at 500 kPa. The specific volume, I don't know. I'm looking for a specific volume, because if I have the specific volume and considering the fact that I already have the mass, then by these two I should be able to find the volume which I'm looking for in part A. So long story short, here the specific volume is my question mark, but anything else I have it. So pressure is 500 kPa, or you need to go to table A1 and obtain R value for nitrogen, and that is equal to 0.2968 kilojoule per kilogram Kelvin. So this is the R for nitrogen and comes from table A1, multiplied by T1, which is 23 degrees C. But just be careful with the units. You need to convert that into Kelvin, to 96 Kelvin. So if you do the math, you will get the specific volume for the left tank, which is 0.1757 meter cube per kilogram. Right? Now, because I also have the mass, then by utilizing these two, I should be able to find the volume. So the volume of the left tank is going to be equal to the specific volume multiplied by the mass, because just look at the units. The unit is meter cube per kilogram. All I want to do is to get rid of the kilogram. So all I have to do is just to multiply these by mass to get rid of kilogram. So that will be 0.1757 meter cube per kilogram multiplied by 3 kilogram, and the volume becomes 0.527 meter cube. So this is the volume of the left tank, this one here. Now I do exactly the same thing for the right tank. So for right tank, I have PV equal to RT. My pressure is 100 kPa. V is question mark equal to R. Now this time I have another R value, because these R's are unique for each gas, right? This is different from RU. RU is a constant number, but R is different. You know where it comes from. It comes from table A1. So R for CO2 is equal to 0.1889 kilojoule per kilogram Kelvin multiplied by the temperature, which needs to be converted into kPa, and that will be 296 Kelvin. So the specific volume, you know what, in the previous Oh yeah, that is correct. So the specific volume becomes equal to 0.5591 meter cube per kilogram, and the volume of the right tank becomes the specific volume 0.5591 meter cube per kilogram multiplied by the mass of the gas, which is 2 kilogram. So the volume becomes 1.11 meter cube. So this is the volume for the right tank. All right, so we have answered part A. In part B, the question is asking for the final pressure. All right, now in part B, what we have is, as I said, a dumbbell shaped tank, but still that's a rigid tank, right? So this is the tank that we have in part B. It looks weird, but yeah, that's the way it is. Equation wise, I can use PV, uppercase P, equal to N RUT. Okay, so in one video, I completely explained about like the difference between this equation and this equation, the difference between these two equations. I already discussed about that. Just be careful. Here is a specific volume. Here, this is volume. On the right hand side, I have RU. Okay, so this RU is a fixed number, and this N is the number of moles. All right, so here's the problem. I am looking for the final pressure of the mixture. So this is my question mark. All right, my goal is to utilize this equation to find P. I am good with V because V is this volume plus this volume. In the previous step in part A, I obtained these two volumes. Let's assume that the volume of the pipe is negligible. All right, so let's assume that the total volume is this volume plus this volume. So V, I'm good. T, I'm good because the problem statement gives me the final temperature. So that is the temperature of the mixture. So here I'm good. RU, I am good. 8.314 kilojoule per kilomole Kelvin. So everything is good except N. And N is the number of moles, which is the number of moles here plus the number of moles here. So that means before utilizing this equation, I need to find how much mole I have on the left tank initially, how much mole I have on the right tank initially, because at this time there is no left and right, there is just one tank. All right, so let's do that, and that is pretty simple. So my goal is to find the number of moles that I have for nitrogen as well as the other gas. So the number of moles in nitrogen is the mass of nitrogen over the molar mass of nitrogen, which is 28.013 kilogram per kilomole. Okay, what I'm trying to do, just look at the units. I have kilogram here and I have kilogram over kilomole. So this kilogram cancels this one, and because I have kilomole in the denominator of the denominator, so that comes up, and then the total unit is going to be kilomole. All right, and this is exactly what I'm trying to find, is 0.107 kilomole. So this is the number of moles I have for nitrogen. I do the same thing for CO2. Mass of CO2 is given at 2 kilogram. The molar mass, this was the molar mass, by the way, and if you are wondering where it comes from table A1. Like most of these properties we are getting from table A1. So this is from table A1. The molar mass of CO2 also comes from table A1. All right, so now these are the number of moles that we have for each component. So that means my N in this equation is this number plus this number. In fact, you know what? I should have mentioned that this is N of the mixture. So it doesn't hurt if we add a subscript M as in Mike to this N as in Nancy. All right? All right, and NM is this number plus this number. So NM m is 0.107 plus 0.045 kilomole, which is equal to, I do not have it on my notes. Let me calculate it real quick. Point 152 kilomole. Okay, now let's get back into this equation, because we have at this time, now I can check this Nm. All right, so if I get back to that equation, then P is still question mark. V is the sum of the two volumes that I obtained in part A. So that will be 0.527 plus 1.11 meter cube. So this, the entire thing is my V. Right, I mean this V. And then is equal to Nm, which is this 1.152 kilomole, multiplied by Ru, fixed number, multiplied by the temperature, which is once again the final temperature or the mixture temperature. So maybe it doesn't really hurt if you put Tm, just to make it clear that this is after mixing. And that final temperature is given in the problem statement. Okay, all you need to do is to convert it into Kelvin. That will be 296 Kelvin. So you do the math and you will end up with pressure equal to 228.5 kPa. So this is the pressure after the two components mix with each other. Okay, now let's go back into the original schematic. Initially, the two pressures that we had were 500 and 100, all right? The mixture pressure is 228. It does make sense, so this number is between the first two pressures that we have. We cannot really double check our work, but it just tells us that the answer makes sense, all right? So, as I said, this problem was exactly similar to, not exactly, but concept-wise was similar to the membrane problem we had. We had a rigid tank. There was a membrane between. The membrane ruptured. So the concept-wise, these two problems are exactly similar to each other.